Young inequality for several functions. But then organizers asked me to speak about Boolean cube. I'm happy to speak about Boolean cube. And the second thing is that I added some new slides, so it will not be completely boring. So this is based on series of joint works with Alexandros Eskenazis, Ramon Manhandel, Fedja Nazarov, Roman Yoshini, Alexander Goldberg, and Xinyuan Xie, who is my graduate student at UCI. I want to start from the quote of Jean Bourgain. It's a screenshot from his paper where he says that over recent years, a new area in harmonic analysis has emerged, which is the Fourier analysis of Boolean functions. It is indeed a new field, and there are many questions, many open problems. It's easy to state these problems. You need zero background in mathematics to understand every problem stated in this field, but there are not enough tools to try to solve these problems, and every time you have to come up, invent something new. So I want to start from the following very basic question. I will have a Hamming cube. It is 0, 1, strings of length n, x1, x2, xn, and they take only two values, zeros and ones. And the basic question I want to talk about is that I give you any function of the hypercube of dimension n, which will be real valued. Sometimes they will be Banach space valued. Sometimes they will be Boolean valued. And what I want to understand is what can you say about the error f minus g, where you take infimum overall functions, actual overall polynomials g on Rn of degree at most d, and then you compute the maximum over the points of the hypercube, over the maximum of the points 0, 1 to the power n. What can we say about this error? And here's one example. If you take this specific function, minus 1 to the power x1 plus x2 plus xn, it's a function of the hypercube. And you subtract these polynomials of degree d, and then you take the infinity norm, and then you ask, when is it less than 1? Strictly less. I want 1 because if you subtract 0, then the value is 1. So the only non-trivial question you can ask, when is it less than 1? And if it is less than 1, then necessarily g is a polynomial of degree at least n. And g, when restricted to the hypercube, it will be of this form. Since you have a polynomial and you restrict to the hypercube, you can always, without loss of generality, assume that it's a multilinear polynomial because xi squared equals xi when the xi takes 0, 1 values. On the high level, the questions I will be discussing, they are really about multilinear polynomials. So now I want to define degree of a function on the hypercube. Degree is the minimal degree of a polynomial p on Rn, such that if you restrict this polynomial on the hypercube, it coincides with f. And as I said before, you can always, without loss of generality, assume that p is a multilinear polynomial. And there is a very interesting activity of finding degree of some functions on the hypercube. One folklore, I will say that if you know degree of a function, then you can say something about the quantum query complexity. You can say that, for example, quantum algorithm, which computes exactly, it makes at least degree f divided by 2 number of queries. So if you know degree, you know some information about quantum query complexity. And here is one question, which, as I said, zero background in mathematics is needed to understand. So we don't know what is the total number of Boolean functions of degree. This is open problem. Another question. If I give you a Boolean function, which is symmetric meaning that it doesn't depend on the permutation of x1, x2, xn, then can you show that it has a large degree? Its degree is almost n. Okay. And I want to start from partial results, going back to this question I asked. There was a recent result, celebrated work of Hao Huang from published 6 years ago. He resolved sensitivity conjecture. And another equivalent formulation of his theorem is that there exist two constants, C1, C2, such that for any Boolean functions, this difference is at most C1 divided by degree to the power C2 and times S of f. What is S of f? S of f is sensitivity of a function. You take the sum f of x minus f of xj. Xj means that on jth position, you flip the bit. If it was 1, you put 0. If it was 0, you put 1. And then you sum up overall directions, overall differences directions. So his theorem is equivalent to this kind of Jackson type inequality on hypercube. But I'll be asking, what about for any real valued functions, not just Boolean? In his statement, it's important that f is Boolean. Is this true? This was the question I was curious about for a long time. Some of my colleagues were asking me, so I was asking some other my colleagues, and I was convinced that the answer will be yes, that this has to be true. And I will show you a couple of reasons why. There is a theorem of Wagner from 1970. It corresponds to the case d equals 0. In case d equals 0, okay, you should think here like d plus 1. You don't really divide by d when d equals 0. He proved that if in the case of d equals 0, you can bound from above by sensitivity of the function. So when d equals 0, this is true. And there is also not very difficult theorem to show that this inequality is also true if function is symmetric. If function is symmetric, you can prove this kind of Jackson type inequality, and moreover, 1 over d is sharp. But in these talks, I won't be really caring about sharp powers. I just need some power, some decay. I will be interested with some. I would be very happy with having some decay. So it is true when for Boolean functions. It is true for symmetric functions, real valued. It is true in d equals 0, so it has to be true. I was convinced that one should be able to prove this. Such a statement that one proved. And before I go to the, before I continue, I want to say there is absolutely no loss of generality. There is absolutely no reason to study p equals infinity case. So infinity, you can ask LP case. And in LP case, there is this conjecture of Mendel from 2012. If p is between 1 and infinity, can you show that there exists a constant which depends on p, such that this difference is bounded from above by Cp divided by t and times LP norm of the Laplacian. And Laplacian is defined like this. So the only difference with respect to sensitivity is that I don't put here absolute values here. It's just the sum of the differences. But for Boolean functions, what happens is that absolute value of Laplacian equals sensitivity. Because if it is Boolean, it takes two values, right? If f of x is, let's say, 1, then you are subtracting either 0 or 1, so it is always non-negative. It doesn't matter if it absolute value. Or if f of x is 0, you subtract 0 or 1, it's always non-positive. So absolute values for all of them will be the same sign. But I did not want to put Laplacian because that theorem is called sensitivity conjecture. It was called before it was solved. Okay. Yeah, the problem is also open, and there are some partial results. One is due to Meyer. Okay, here I care about power. I want power 1. I don't want some positive power. When p is between 1 and 2, then alpha p equals 1/2. This is due to Meyer. And alpha p equals this complicated expression when p is 1 infinity minus this interval, or except 2. When p equals 2, this is a trivial problem. And this is due to Eskenazi and myself. And when p is, and later it was resolved that when p is between 3/2 and 3, Nazarov and
Repart, stupid question. Maybe you defined it, but I missed. What is your x to power j?
x to power j is this vector x1, x2, etc. xj, I flip the bit. I write 1 minus xj. xj, I just flip the bit. For example, if my vector was 1, 1, 1, 1, then x to the power 1 will be 0, 1, 1, 1, 1. Any other questions?
Yeah.
Yes.
Is it clear what it means if Laplacian of f is identically 0?
It means that the function is constant. Laplacian of f is 0 if and only if the function is constant. But there are many eigenfunctions of Laplacian of f equal to lambda f. This means that it is L homogeneous polynomial. It's multilinear polynomial where each monomial is of size L. Okay, we don't have harmonic functions. Non-trivial harmonic functions. Okay, any other questions? No. And sometimes on even days of week, I believe that this is sharp and it cannot be. On odd days of week, I think that this is wrong. Maybe power 1 is correct. The conjecture of Mendel-Noah is correct. So I'm not sure. Maybe I should ask ChatGPT. They make pretty good guess sometimes. Okay. And this interval, it's extended to this interval. It was using this complex hypercontractivity. It was proven for this interval. It's a very nice tool. I think it is the only tool used in Boolean functions when trying to do some estimates. And we showed this complex hypercontractivity. It was based on conjecture, and then we were able to extend this power to this interval. You know, you can ask also questions, what about Banach space valued functions, when a function takes values in an arbitrary Banach space? By the way, this LP norm, they are, I will be thinking that they are with respect to the uniform probability measure on the hypercube. So you sum up overall vertices and you divide by the total number of vertices. And in Banach space valued case, so now the right-hand side is slightly different, but it is very similar to Laplacian. When Banach space is realigned, they more or less coincide. It is gradient, not exactly Laplacian, but there is this boundedness of Riesz transfer. You can reduce it. They form from each other, so it's almost the same thing. And in Banach space, we have this inequality that this holds for all functions. If Banach space has finite cotype, this was Pizier's problem. He was trying to solve Enthal's conjecture, and he had a program and he wanted to prove this inequality with really for any Banach space with some universal constant, but he proved it with log n. N is the dimension of the hypercube. And he wanted to remove log n, and then Talleyrand came up with another example showing that the log n is sharp. And that program kind of failed. But now we show that to have this inequality with dimension dependent constant, then the Banach space must have finite cotype. If and only if case. Okay. And there is also similar inequality. Not quite similar, it's a different. But, you can put this kind of derivative on the right-hand side. And this is true if and only if Banach space has type P. And this inequality is also Enthal's conjecture. But it's a different story. I will not be going there. I'm just saying that when d equals 0 and you ask this question for vector values, they were very interesting questions and they were open for some time. Okay. So going back to the previous real valued case, p equals infinity, where I have sensitivity. So the answer turns out to be negative. I was expecting that it should be true because it's true for Boolean functions, it's true for symmetric functions, it's true for d equals 0. I don't know. All the examples I know it was true, but it is not true. And there is a counterexample. And it says that if degree is actually less than 0.499 times n, then this difference doesn't really decay to 0. If you fix sensitivity is 1, you can always, without loss of generality, assume that just divide by constant. It doesn't decay, it doesn't go to 0. So in Huang's theorem, it's very crucial that it's a Boolean function. Booleanity somehow plays some role. But then once you have this statement, you ask what is so special about 0.499? It's just any constant less than 1/2. You can put any constant c less than 1/2, c times n will work. What about if it is greater than 1/2? Okay, let me see. Right. The same inequality holds if I take infimum over any subspace of the same dimension, like the dimension of these polynomials. You take L2 on the hypercube with the uniform measure, you take a subspace if it has the same dimension as the dimension of polynomials, and dimension of polynomials of equals to this is exactly this, then it is also true. Polynomials are not important in this question, in this counterexample. What about when degree is greater than 0.5? Then, is there really a threshold? What is going on? And there is another theorem with Verschieden and Shea where we show that if you put 0.5, then the dimension of these polynomials of degree less than 0.5 is exactly 2 to the n minus 1. We don't know the answer exact for polynomials, but if you just talk about the subspaces of that dimension, then the answer is now kind of positive to the first question. As soon as dimension is 2 to the n minus 1 or greater, then there exists always a subspace such that you don't have counterexample. You cannot consider counterexample. But there is, you can ask, when you don't know how to solve the problem, you ask what happens in random case. What happens for most of the functions? And there is this theorem from 95. It says that at least 50% of Boolean functions satisfy this inequality. But n over 2 is great. This error is at least 1. 1 you should put here because the value is minus 1, so absolute. And this n over 2 is sharp in this random case. There is another theorem of Ryan O'Donnell, Servadio from 2008, that at least almost all of the Boolean functions satisfy this inequality. So as long as you add little bit, square root of n log n, it is less than 1 over n to the power to decays very fast. Okay, so maybe 0.5 times n is indeed the sharp threshold in the polynomial case, in the deterministic case, but we have no idea how to show that. But we have something else, and I'll show you when we talk about approximation by high degree polynomial. Let's say that if degree is greater than n over 2, we are talking about high degree polynomials. When degree is less than n over 2, we are talking about low degree polynomials. In high degree polynomial case, we have this theorem that this difference is less than sensitivity, what we want, times something, and that something is, so you take any polynomial on the real line of degree at most t, and x is a binomial distribution, but normalized 1 over n, and you can put always this factor. So there is this freedom to have this factor, and then next question you can ask, what's the infimum of this over all polynomials of degree at most d? And we computed it a little bit, but I'm not saying it is sharp. Maybe there are better bounds that one can get. we can show that this infimum is at most C times minimum delta maximum delta to the 2 of this expression, what you see. But my point is that when D goes to N, when D approaches to N, you should expect the right-hand side should go to 0. And that's what you are getting. When D goes to N, this delta goes to 0. And this right-hand side goes to 0. So you are getting approximation. But I don't think that this is sharp. Maybe one can improve this result, but this is what we have at this moment. My student is still working on this question. I want to show you some applications. The first application is like this. So let's define approximate degree. Given a function on the hypercube, I will say that D is, let D be the minimal degree such that this difference is less than 1/3. Let's think that F is Boolean function. It takes two values, +1 or -1. So minimal degree so that this difference is less than 1/3. If you put something D -1, then this difference will be greater than 1/3. And Huang's theorem in his original formulation is this theorem that sensitivity is at least square root of degree. But the conjecture was open, it wasn't about square root, it was about putting some power on the degree, just putting some power. Sensitivity is at least degree to the sum power. And he put square root and it is sharp. Square root is sharp. You can ask, is this true for real valued functions? The answer is no. Booleanity is important. And here's a very simple counterexample. You take -1 to the power x1, etc. Part xn divided by n. And sensitivity is 2. It's not difficult to check. Degree is n. So sensitivity stays bounded. Degree is large. There is no chance. But what about if you replace degree by approximate degree? This question is non-trivial. Because why this example worked, it had a large degree, but it was taking very small values. I divide by n. And can you have something like this if you replace degree by approximate degree? And this was not known for a while. And one application of this theorem that I presented in the previous slide is that there exists a function which takes values in the interval 0, 1, with sensitivity at most 1 and approximate degree very high. So there is also no chance for this kind of inequality to hold on the high. Another application goes back to this Mendel-Nauer conjecture back. Actually, that Mendel-Nauer conjecture is one of my favorite problems. First time I learned about this problem, I was a postdoc of Fedzi Nazarov at Kent State, and he told me about it. Well, I'm still thinking about the problem. Since then, we made some progress that on the real line, equipped with the standard Gaussian measure, that the analogous inequality is true, that this Mendel-Nauer's conjecture is true on the real line. That is the state of the art, but on the hypercube, we still don't know. So here is a little bit of Fourier analysis. Any function on the hypercube you can write as a Fourier Walsh series, f hat of s, ws. Ws are these Walsh functions. S is a subset, you sum up over the subsets. And these are orthonormal system with respect to the uniform measure on the hypercube. And Mendel-Nauer show that infimum of L1 norm of f divided by the Laplacian. And you take, supreme. You take overall functions which live on high frequency, on frequency greater than log n. So it's a sum of the sets of cardinality, this log n. Then this is separated from 0, independent of n. It's separated from 0. This in particular illustrates that Mendel-Nauer's conjecture is not true at the endpoints when p equals 1 and p equals infinity. The analogous question on the unit circle is true, including p1 and p infinity for trigonometric polynomials, but this is a different story. There is something going on at the endpoint case. We have some singularity and we need to detect and somehow deal with that. So this was the counterexample, and our theorem shows that there is slightly better counterexample. That now supremum is still separated from zero, not frequency is greater than log n, but actually frequencies, it's much small class, greater than 0.499 times 10. Okay, may not be very impressive application, but it was something important to understand if you are working on this Mendel-Noor conjecture about this Jackson inequality with sharp K1 over D. It's good to know about this example. I want to slightly deviate and also discrete approximation theory. This slide will be, and tell you very basic question in learning theory. I give a function f. Actually, I'm not giving you a function. It's unknown function. I'm hiding it from you. But you have an axis. You have the following axis. You can query the sums. You can query x1 f of x1. Now this one on the top, it doesn't mean I flip the bit. It's just a random variable from the hypercube, chosen uniform random variable. x2 f of x2, so you are sitting in front of computer, you press the button, you see the input, you see the output. And you press the button, you see once, you press the button, you see the second time, and then you can do it several times. You are getting these samples, you are learning some information about the function. And the question you want to ask, is, knowing these samples, can you come up with the function on the hypercube, which would approximate your function in L2 up to epsilon error? Of course, the question doesn't make sense because it could be that you are querying one and the same samples every time. You just see one and the same points, then the answer is you cannot learn anything. So what we add is that we want this with high probability. Because these samples are chosen uniformly random. So, okay, you didn't succeed first time, but you are succeeding in many, many times. You want this with high probability. It's a random function, h, which depends on the samples. These samples are chosen x1, x2, xn are chosen in each other. It's a random function. And this is the first basic question in learning theory on the hypercube people ask. And here is also, you want to put some assumption on the function. It cannot be arbitrary function you are trying to learn. You want to assume that it is from certain class. It has some low complexity measure. There are simple trivial examples to construct that there is no way you can come up with any algorithm which does a good job. You can always come up with very bad functions. So you want to assume something about your functions. And what I will be assuming is that my functions will be taking values in the interval -1, 1. They will have degree at plus d. So they will be bounded degree d polynomials. And the first theorem says that you can learn this class. You can learn this class with L2 error epsilon confidence 1 minus delta in about this number of queries. There is some constant which depends on epsilon, delta, d, but the main constant is this one, n to the d log n, which is pretty big. And the reason you see n to the d, because if you take your function, expand into the Fourier-Wolf series, maybe you want to learn the Fourier coefficients and then just write the sum. And how many Fourier coefficients does degree d polynomial have? It has n choose 0 plus n choose 1 plus etc. n choose d, and this sum is almost n to the d of order n to the d. There is this extra logarithmic factor, but it comes from probabilistic side. And recently, in 21, there was this result of Rao Reis Rathos Yehudeo, who managed to decrease slightly, got n to the d -1 query. So they say that now you need this many queries. But if there is n to d -1, then there is the question, what is so special about 1? And what we showed right after several months after this result was published, we showed that there is this constant, but you can ignore for a moment. It is of order log n. So we removed n to the d. You don't need this this big number. Low degree polynomials can be learned in logarithmic number of random queries. I'm not talking about the how long does it take to construct this random function. I have no idea. I think it takes it's not about runtime, it's about query complexity. It's how many queries you assume that you have huge computational power. Assume you have. What can you do with this computational power? You can do everything in very little number of queries. And in this estimate, in this middle line, I wrote this constant, bhd to the power 2d. bhd to the power 2d. And I want to say a few things about this constant. It comes from Bohnenbus-Hilo inequality. So we used something that was never seen in this learning theory field. It comes from the Fourier analysis. Actually, before I move to the next slide, I want to show you, I want to say that if you look at the proof, essentially all the proofs, they really use the Fourier analysis. Fourier analysis that you learn the Fourier coefficients, the way you construct this random function, you learn the Fourier, and I don't think there is any other way to come up with a better construction, because there is another paper due to Eskenazis, myself, and Lauritz from Cambridge, which says that this log n is sharp. You cannot do better than log n. But then the next question is, okay, what about these constants? So in n it is sharp, what about in d, in epsilon, in delta? And I think the first step to do is to improve this constant. And what is this constant? It's this Bohnenbus-Hilo inequality. You take your function on the hypercube, you write it into a Fourier Bush series. You have Fourier coefficients, you take, and let's say that this function is of degree at most d, so it's a multilinear polynomial of degree at most d. Then if you take this norm of the Fourier transform, then it is bounded by some constant times L infinity norm of f. Everything is happening on the hypercube. So we live in this Boolean cube. And there was a question for a long time, which was saying that, can you even put a constant which does not depend on n, but depends on d? And this was open for a while. And then it was proved that the answer is yes, that you can put some constant, which only depends on n. This is the constant I have in this learning algorithm. And there is a current record which says that this constant is bounded by some big constant to the power square root of d log d. I believe that the answer should be here 4. You can replace it by 4.
What's the motivation for the plus or minus 1 in the notation?
Because about Boolean cube, we are talking about plus minus 1 to the power n. There is also the same inequality on the torus of dimension n. There is the same inequality on the about matrices. And whenever you have this kind of inequality, you always get as an application the query complexity in learning. You can learn trigonometric polynomials, so you can learn the matrices as soon as you have this kind of inequality. Right. I'm saying that one should be able to put here 4. I would be happy if you put here d to the power 100. At this point, we have little bit sub-exponential. Wrong. And it's a very interesting thing that it was used to identify the Bohr string or Dirichlet series. It was used to identify the Bohr radius for multivariable or polynomials of many variables. Okay, I don't want to go further, but I'll just jump to the next slide. Let's see how much time I have. So I want to show you proof of one of the results. I'm not saying it's the most highlighting proof, but it is just to give you a feeling what kind of tools we use sometimes in this field, what is going on. And let me show you the proof of this bound. Here I replaced a binomial distribution. I put 1 over n outside. Now it is not normalized. Inside the polynomial, it doesn't matter, just this scale. But because of this x, now I put here n. And let me show you just one random proof. So you can assume that the polynomial has average 1 with respect to this distribution. And let's take a polynomial on the hypercube, which is just this polynomial on the real line, but you put this argument x1 plus x2 plus x. It's a function on the hypercube. We can show that it's a polynomial, it's a multilinear polynomial of degree at most d on the hypercube. Then there is this standard thing we do in Fourier analysis. Let's take a convolution, and it should be a best approximation. It's about finding the correct curve, right? That's how to proceed. And in this case, it little bit works in L infinity case, but in LP case, I don't believe that it's the best approximation. It's a convolution type in LP case. But I'm not even sure in this case. So if you take, this is the convolution. So you take average of f of y, h of y. This plus means that you add coordinate wise, x1 plus y1 modulus 2. And then you can say that this maximum is attained at some point x star. Let's assume this maximum is attained at some point x star. You can reduce to the question when x star is the vector 0, 0, 0 by making small change of variables. And f of x is little f of x plus x star. And notice that the sensitivity doesn't change. So we are really having x star equals 0. Then what is happening next? I take expectation outside. I put absolute value on h. And I just wrote down the definition. So what is it? It is exactly this sum. So here I'm summing up overall points y on the hypercube of Hamming weight k. So it's y1 plus y2 plus yn plus k. And I look at these differences. About capital F, you can think of it as just a function, arbitrary function of the hypercube, arbitrary function. And pk, p is my polynomial on the real line. And there is this normalization constant. And then we have this lemma that this difference you can bound as 3 times sensitivity times this binomial coefficient. And once we have this, then it's very easy to finish this estimate. So you will just take this and replace by this, and then you sum up this. And then whatever the expression you get, it's exactly the reason you see this binomial distribution. So you can recognize that this interesting sum is just average with respect to this binomial distribution. And the way we prove this lemma is like this. Assume that sensitivity is, by some reason in this proof, there are 2 cases when k is less than n over 2 and when k is greater than n. The proof just breaks down, I don't know why. Let's focus to the case when k is less than n over 2. Sorry. What you can do is, so you have difference f of 0 minus f of y. You can write the following telescopic sum. You can take all paths starting from 0 on the hypercube and going up always, or maybe staying on the same level, but never going down. So these are monotonic paths going up along the edges and joining 0 with this point y. And then you can sum up, you can write this point minus this as the difference. So you have this path. The first thing you can do, you will write sum over all paths, and then you just normalize, divide by total number of paths, 1 over k factorial. And then the difference along the path, so starting point, end point, you can write as telescoping this. So if it is the edge, so f of 0 minus this, you can write f of 0 minus f of next vertex, and then f of that vertex minus f of next vertex. And then you just put the absolute, you do very rough estimate in this argument. So where in your overall vertices from you start from 0. The last point is y. You are joining this 0 to y. And so we are talking about neighbor vertices. So Hamming weight is 1. And when I said you always try to go up, you never go down, that's what it means, that component-wise, AI is the vector on the hypercube, so each coordinate is greater than the corresponding coordinate of the previous AI minus 1. So you can write this as like this. And then there is a simple lemma saying that the sum overall paths joining 0 to 1 and the sum of these differences normalized by 1 over k factorial, you can write like this. Sum overall points of Hamming weight less than k minus 1 times, sensitivity at point x times some constant which depends only on the weight, on the Hamming weight of this point x. It's not difficult to see why you must have you could have something like this, because you just look how many times the difference along a certain edge occurs on the left-hand side. And you could see also what happens on the right-hand side, how many times that difference with respect to that edge occurs on the right-hand side, and you just make them equal. And you get this from that system of equations, you recover the values of PL, it will be this. So there is nothing really difficult in this at this stage. And then you show that this sum with these coefficients inserted here, which is this sum, it's bounded by this binomial coefficient when k is less or equal n over 2. And this is not true if k is close to 10, this fails. It's not about this constant 2, it just fails catching the correct growth. Right, and that finishes, you can show this in the code, that finishes the proof. When k is greater than n over 2, we use Wagner's theorem. In particular, his theorem says that for any function of the hypercube, the difference between at the 0 and at the vertex 1, 1, 1 is bounded by maximum sensitivity. So you just subtract, you had in the beginning, you had f of 0 minus f of y, so you add f of 1, subtract f of 1, and then f of 0 minus f of 1 will appear those many times, which luckily is the same binomial coefficient, and f of 1 minus f of y, you do the same argument. So you flip back to the points, you do the same argument like before, and then you prove this in the code. Is it sharp? If your function is monotone, all the steps done here are sharp because these differences, these absolute values I put, they are non-negative. Okay, I guess. How much time I have? 5 minutes. Okay, I'll stop here and I'll.
Okay, thank you. Time for questions.
Said there are many questions, conjectures in this field that are easy to state. Do you have a favorite conjecture?
Yes, I have my favorite conjecture. Aronson and Bailey's conjecture. It has very nice implication whether quantum algorithms can offer exponential speedups over classical algorithms on certain number of problems. So, it says that for any function, let's say -1. So there exist constants, actually, so there exist constants C1, C2 greater than independent of anything. Okay, let's write like f of x minus f of x j in this case, I flip the bit, is greater than the variance of f divided by d times it, where variance is I give you any polynomial, it's a multilinear polynomial of degree at most d, and the question I ask is it true that you can find constants here and here, so that this is called influence, L2 influence, so that max influence is at least variance divided by d, so that maximal influence is big, even though it's by d, but for 1 degree polynomial, it's big. And this is my favorite problem. It was recently announced that it was solved by Geller and Klein. And people are writing in Twitter, on social media, that finally Armstrong Rings conjecture is solved. And positively solving means that quantum algorithms are not offering exponential speedups over classical algorithms for certain number of problems. For certain number, I'm not explaining what does it mean. And there was a mistake. I sent email to authors. They accepted mistake and they withdraw the paper. So it is still open.
Can you give some intuition about why, even though there's like n to the d Fourier coefficients, you can learn in only log n many queries? Or even just like anything less than n to the d?
I think it is equivalent to, can I give you intuition why in von and Busch-Hill inequality there is this power to d divided by d plus 4?
I can.
You can. Okay, what's your explanation?
So those guys, they invent this random algorithm using Fourier coefficients, but they sort of estimated Fourier coefficients by one. And there are n to the d. And this Bonin-Busch-Hill inequality shows the estimate for all of them together, a certain norm, which is enough to eliminate n to the d. Is it okay?
I will just say that if you come from analysis side, you are interested. I think von and Busch-Hill inequality is a question for this outputs, not for computer science people. So improving the constant in von and Busch-Hill inequality will improve this algorithm, the second part. So it is interesting question.
If not, then let's thank the speaker again. And we now have the conference photo, so go away, but we go off.